adapt. I know that you had the presentation last week about domain adaptation, so what I will try to do is to, well, tell you some of the new things that there are in there. So not only classical domain adaptation. I will skip some of the slides because I have too many of those. But I will concentrate on, let's say, the new things in which you have multi-target, multi-source, in which you have no access to the source data, and all these type of situations in which I believe they are closer to real life. And well, this work, it's usually done by my colleague Elisa Ricci. She is the one in charge of, let's say, domain adaptation. But we are sharing many of the students, and when we've done together, we have a lot of discussion on this subject. Okay, so very quickly, just to have a brief introduction. Well, one of the main limitations that we have in general with our learning system is that they are not data efficient, right? So we are requiring a lot of labeled examples. And the main problem is that in general, the model do not generalize well to the new domains. Like, so unlike humans, they are having troubles to do this generalization, right? So if you go to well, a situation like in a autonomous driving situation in which you have, let's say, the summer conditions, and then you want to adapt to the new domain in the winter conditions, most of the domains, unless you do something special, most of the models will have troubles. Okay, so you're not trained on some conditions, and then you are asking to label and to test on another condition, and then you have to deal with what is called dataset bias, domain shift, and so on. Okay, so very simple example: if you do some sync segmentation, if you train and test on the same data set, of course on different domains, so you have the training domain and the training set and the testing set, it's working pretty reasonable, right? You can see you have road, people, and so on. The problem is now if you apply the model that was learned on cityscapes and you put it on San Francisco dashcam, okay, the conditions are different, then it's really giving you complete crap. And you see, you can get some road stuff, but then you get some trees, but you get some trees on the lower side and so on. So it's going very, very bad. It's even worse when you go to, let's say, a situation like this, and in which you are in a tunnel, and since in the cityscapes there are no tunnels, then it gives complete garbage in there. Okay, so you have to do something about it without needing to do a lot of training and a lot of things, you know, to do the things on your data set. So one of the main reasons for this is that indeed the distribution of your source domain is different from the distribution of the target domain. So one of the classical approaches is really to start to do alignment of the distributions. Okay, so in the source domain, you have a lot of label data, while in the target domain, you have unlimited or very, very limited labels. So you want to practically, what you want to do through your adaptation model is to kind of give labels to the images that you have in there. And this may look completely different from what you have in the source domain, right? If you go from the, let's say, some kind of cartoonish type of things that you would have in your source domain, so in the ImageNet, you want to put them into real life, and they will look completely different. Okay, so, well, it is a long-standing problem. You start with training. You have a few categories that you are using for training. You learn a neural network, and then in a testing domain, you just give a new image, and you want to classify it as a bag. And it's working as long as it's kind of similar to what you have in the source domain. But then if you have something different, then you have troubles to try to give the label. Okay? So what I said, this is the domain shift, because let's say the two domains are different. So these are real images. The other one are kind of cartoon images. Or because you have different conditions like weather or whatever, illumination and other type of things. Okay, so, and then of course domain shift is it's ubiquitous because you can do things when you have the time and environmental changes, you have different modalities, you have synthetic to real images, you can have some CAD to real images and so on. Okay, and then of course applications are quite a lot. So these are just some examples. You can do it for recognition. You can use it for segmentation, for detection, for example, in some sort of, you know, in an autonomous driving type of scenario. and you can do it for re-identification even if the domains are completely different. Okay, so what we try to do is to do this learning with domain shift. Okay, and the most important, the easiest way we'd want for us would be to try to do this unsupervised domain adaptation, right? So we don't want to be able to, we don't want to start labeling the data into your target domain. So you want to work it completely without us doing any intervention. Okay, so we assume we have no target annotation. However, in the classical domain adaptation, one of the assumptions, and this is a strong assumption, and we'll talk next about how to release this assumption, it's the fact that we have the same categories into both domains. And this may be true in some particular situation, I don't know, autonomous driving, so that was the example with Cityscape and, well, San Francisco Dashcam. But in other cases, it's not necessarily true because you may not know what you have in your target domain, or you may not know on what sort of categories your model have been trained. Okay, so this is what I will concentrate on today, and that's why I will skip some of the slides of the classical domain adaptation. So let me get into that. So again, so this is a simple problem. The distributions are different, from the source and the target. And here, what I said about the assumption, you assume that the labels from the source are equal to the label from the target. Okay, and well, you have the same. The domain are different, but you have the same watch, badge, bike, and whatever you have in there. So if you look for some kind of taxonomy of traditional domain adaptation, so this is a survey. It was a transaction on knowledge and, discovery. So what you have, you get from transfer learning, and then they say, well, if you have labeled data and available in the target domain, then you can go towards inductive transfer learning, and you have, self-taught learning and multitask learning. If you don't have the data, you have the data only in the source domain, then you can go toward domain adaptation or unsupervised transfer learning. So this is some sort of taxonomy. It's not perfect, of course, because you may have methods that are kind of shared between different things. And there are many domain adaptation strategies. So one of the classical one, probably you see also from the references is probably the older one, it's metric learning. But then people were kind of looking at subspace representation. And you are considering here with the subspace, you are allowing to consider that the entire data in one domain as a single entity. And then you kind of look into some sort of Riemannian manifold in which you are looking, and you are getting samples along the geodesic between the source and the target subspaces. And this is quite an effective type of approach, but they only indirectly address the domain shift, right? So practically what you do, you have this manifold to kind of bring together the source and the target domain data, and then you have some kind of connection into the geodesic between the domains. And so, as I said, this is just an indirect approach, but now what people were considering after that is trying to aligning the distributions. So kind of ways to align the distribution. And there are, well, many ways of doing it. I'll have in the next slide. Another thing that is important for domain adaptation is the presence of benchmarks. And there are several of these benchmarks. So this is, well, a few of the data sets. So you have, Amazon data set, DSLR, webcam, and so on, in which you have several object categories, different domains, different type of features, and so on. And then, of course, there are different domain adaptation methods. So this is just an incomplete list of paper strategies and so on. I will not concentrate much on this. Some newer benchmark is more like a domain net data set. So here you have far more categories. You have 356 categories. You have 6 domains. And, well, you have different semantics categories, and you see the difference between them. Like food, you have cartoon, real images, different conditions, and so on. And the type of method that you could consider are, like you see here, adversarial reconstruction, discrepancies of supervision, normalization, and so on. So there are many other approaches that exist that do not belong to one of these categories. Okay, so let me skip some of the slides because here I have, the slides will be available so you can have a look through all this, but I want to concentrate on, let's say, the situations a little bit more specific. So one of the main ideas, one of the main problems with the classical domain adaptation approaches were that there are too many assumptions. So one assumption is that there is a single source and a single target domain. Another assumption I already mentioned is that there are a shared label space, right? And yet another assumption is that source data is available at the training time. But then, of course, if you think about it, in many conditions, this cannot be possible and cannot be available, right? So if I want to, for example, share a model, a trained model with you, I will have to share also my training data, which is not really feasible. In many cases, I cannot share the training data because I'm not the owner of the data, so I cannot just share it with you. So you have to cope, and this is what I will go into this hour. You have to cope with situations, different situations in which you have to relax these assumptions. Okay, so let's start slowly like this, so we go, let's say, from kind of simpler to a little bit more complex. At the beginning, we consider we have multiple source domains. Okay, so this is called the multi-source domain adaptation. And this is kind of reasonable, so why would I have to consider only a source domain? If I have available data and I have labels for it, I can easily use more source domains. So I can have the real world, I can have some art, I can have some product. In this case, as you see, there is exactly the same labels, but I'm using it, I'm using the information from different source domains. And then again, my target domain is still, well, cartoon or whatever it is in there. And then how do you really deal with this type of situation, right? Because you will have to see how you put all the source domains together. You consider them independently, you try to learn from each of them. Well, there are several strategies, right? So, well, you have, so this is more like a standard pipeline. You see a few steps in there. So first of all, you have a feature extractor that will map the target and the source information to a common space. Could be the manifold, could be something else. And then you have a category classifier, which is the one in here, which will receive the target feature and produce the classification based on category in the source domain, right? So this is more like you treat each of the domains independently. And then you have a domain discriminator, which is the one in the middle. So I can also, so you go to the domain discriminator, which receives a feature from the source and the classification from the target, and produce some kind of adversary example for the domain that you want to do, right? So you get the adversary between the target and the source, okay? And finally, you have a perplexity score, which is kind of weighing how important these examples are to your training data. Okay, so then you have the target classification operator, and you keep on doing your stuff. Okay, so in general, what people do, you have this kind of what is called the latent source domain discovery. Yeah, so you have the source domain and the target domain. And you have several approaches. So one, you have a multi-domain assignment layer. So you have two branches. So one of the top branches automatically discover the latent domains. So this is the representations of the source and the target into the same representation. And then the main network uses alignment layers that they will learn before. Another approach, this is what you do, is called the gradual domain adaptation. And it's not indexing in the intermediate domain. Right? So you have some kind of index domain sequence, and you keep on getting the images from the source, and you put them into your, you do this kind of gradual shift that you obtain in there. So this is more like you try to kind of use each of the sources independently first, and then you combine them together in order to obtain a better results. Another thing, it's exactly the opposite. You have the source domain, one source domain, and you have multiple target domains. Yeah, so this is the multi-target domain adaptation. So what you would want to do in here, this is what we propose with what we call the curriculum graph co-teaching. So you need to find a kind of common dictionary. And here, what we do, I have a few of these things. The strategy, it's kind of simple. You go from easy to hard domain adaptation. So since you have multiple target domains, you just choose first what will be the first domain you want to address. So what you do is, the assumption in here, it is you are going to address, to minimize the gap between the source and the target in that way. And then of course, you need to do some kind of target selection. And one criteria you can use, and this is what we were using in here, we were using the average entropy for the adaptation process. So we choose the target domain that has the closest average entropy to my source domain, and I'm doing the adaptation first for that target domain. Once I've done that, then I take the classified images, whatever, the samples from the target domain, and I consider them into my source domain as pseudo labels. And then I keep on doing like that, and then I'm getting the next the easiest remaining domain, and I keep on iterating in this respect, right? So you just repeat this step until for the remaining target domains. And this is working quite well. It is called curriculum graph co-teaching, first of all, because it's more like learning a curriculum. So I'm learning what is some of the labels in my new target domain. I use these new labels, I put them into my source domain, I'm enriching my source domain with pseudo labels, and then I keep on doing the adaptation. All right, so this is more like explaining here, you have some curriculum learning, and then from there you just take from several targets you see there, you are just popping some of the information, and then you create the pseudo labels that you are putting into the pseudo source, and then you keep on going like that. Right, but here, of course, you need to have the domain labels. They have to be available. And, well, of course, in our case, again, the numbers are indicating that, well, we are obtaining better results, even if we have a much more challenging task than, our state-of-the-art competitors. Now, we do have a few other situations in which we have the label space between the domains is different. So this is something that we would want to have. And there are several types of situations in which you would have. Right? You can have a closed set domain adaptation. So here is what we had before. You had all the labels are shared between the target and the source. But then you may have different type of situation like partial domain adaptation in which only part of the labels are shared, while the other ones are not. You have, again, the open set domain adaptation in which each domain, so in the partial domain adaptation, you have some new labels, even though most of the labels are the same, right? So you have the source domain. In the source domain, you have more labels that you would have in the target domain. So the target domain will be a subset of my source domain. In the open set domain adaptation, I do have some common labels. Well, I put in some animals in there, but you also have on both on source and on the target, you have different type of categories, right? And then, so you can have, well, different situations that you see there. Either that they have some common stuff and each of them they have several labels, or you have more labels into the more categories into the target domain. Or what you would have, it's what is called universal domain adaptation, in which practically you have no overlapping labels, or at least you don't know that there are overlapping labels. Okay? So that's why I didn't put any label in there or any figure, because you may not know at all. I mean, I just have it, I try it, and then we'll see how I can do it. Okay? And the goal here is to find a model that generalizes well to all the unlabeled target domains. Well, why is this relevant? Well, because the real world is definitely far more complex and contains more than just a single target domain. Yeah? And the number of the network scales linearly with the number of the target domains. And it's challenging, well, because we have multiple and varying domain shifts. We have non-overlapping support with some target domain. And then we may also have some problem of negative transfer, right? So even if we do the domain adaptation, we can just even hurt our classification. So let's go to let's say, some of the situation like this. So if we do, there are a few of these examples like universal domain adaptation, in which, well, you can do several of the things that you try to do. You can try to hallucinate some of the labels. You can try to discover some the common private label set and adapt in the discover common label set. You can do some domain consensus clustering, so try to kind of go through the labels you have, and you try to see if you can align some of these domains, and so on. Of course, there is no recipe here, so here you have to kind of do some sort of mining and come up with some kind of magic in some way. Okay, so that was one situation. Now we just go to some more complex stuff. So what if only the source model is available? Okay, and this is called the source-free domain adaptation. So you have now, instead of having the images in themselves, right? So instead of having the label, the data set that will allow you to retrain or whatever, understand what is going on in there, I'm giving you only the source domain and nothing else, the source model. Okay, so you still want to do the adaptation in that way because you have already learned something from there. And that will be the situation in which I cannot share with you my training data because it's proprietary, because it's whatever. So the good thing about it is that, of course, if I give it a source model, you cannot just come back to my data. Let's say it could be some privacy reasons or some other kind of reason that you would have. But you still want to use this information to do your domain adaptation. Okay, so there are a few approaches here. Well, I'm going quickly through them. So one is the source hypothesis transfer. It's called SHOT. It's exploiting the mutual information maximization to fine-tune the source encoding model. So you try to kind of do this fine-tuning so that you are mimicking as much as you can from the source information. And then you have this, what is called the EM, so the kind of information maximization, in which makes the target outputs individually certain and globally diverse. So you try to kind of go from the source model, and you try to see if you can match them so that they can some kind of more complex cluster. So that's why you are putting those losses in there. Right, so you are computing here the target centroid for accurate pseudo labels. You can also have what is, again, for the source-free domain adaptation, it's something like, so this is some recent paper in which you have the source-free image translation in which you are adapting the knowledge in unsupervised domain adaptation, and you have two branches. So one would be the original target image are fed to the network. That was the first part. And then you minimize the knowledge distillation loss. Right? So you try to get this distillation loss by minimizing it, what you obtain from the target branch. And you are also considering a relationship resensive loss, right? And adapt the generated network according to these two losses. So if the two branches get similar results while adopting different models, then the difference between the original target image and the generated source image should be able to mitigate the difference between the classifier. And then we will have some sort of adaptation through the network. You see here you have some kind of you are hallucinating some images from the target domain. You are getting something in there, and then you see if you can minimize these two losses through your, you put the generated images through your source model that you have available, and see if you can, by generating that image, you can obtain some sort of close, you can minimize the losses between the knowledge distillation and the relationship preserving loss. Right, so that's kind of, this is a more detailed scheme of what we had before. It's a little bit more complex. You see some convolutional layers there, some batch normalization, and so on, the things that you try to minimize into there. Right, so this is some of the examples in which you can see also some of the things that you start understanding what's going on. This is an ablation study in which you have different, for the baseline, you have practically no focus on the classifier for particular features. Instead, if you add all the things, you can see that you can understand exactly where this, in the visualization, which part of the object is the one that is triggering the adaptation model. You can also do something what we call, so this is a paper we recently had at ECCV 2022. It's what we called uncertainty-guided source-free domain adaptation. So here you have a new perspective. So since we don't have the source data and the domain and we have the domain shift, this would make the prediction of the target data unreliable. Okay. So in order to do this, we are quantifying the uncertainty in the source model prediction, utilizing, and then we utilize this uncertainty to guide the target adaptation. And then, well, you have different inductive bias for the model. You may, in the source model, we may predict incorrect target pseudo labels with high confidence. And this is due to the extrapolation in the ReLU networks. Okay, so in order to avoid this type of things, we are constructing a probabilistic source model by incorporating some priors on the network parameters, inducing a distribution of the model predictions. Right, so the uncertainties are estimated by using a Laplace approximation, and we are incorporating to identify target data priors to, that do not lie in the source manifold. Right, so we are extrapolating towards on the source manifold. And well, at the beginning we have, this is a step A, we have the initial source model training, and then we have the additional step 2 in which we do this Laplacian extrapolation. And then practically what we do, so you are learning these two losses, and you are using the target, the target adaptation in which you keep the posterior over the parameter that you already learned, and train under an uncertainty-aware composite loss that weights practically the samples according to the predictive uncertainty. So here we are kind of looking at the certainty as a guiding score for doing the adaptation. And then, well, again, our numbers are slightly worse than the state of the art, but here the assumptions we have, so at least for the Vista C data set benchmark, we have a little bit lower numbers in accuracy, but of course our conditions is it's far more difficult than the state of the art. For the domain net, we obtain a little bit, so the numbers are comparable with the other approaches, and then you see that it's depending a little bit on the data sets in which you use as a source domain. Okay. So now, so far we assume that everything it's static, right? So you have the domain, you have the target domain available and it's not moving. But what if now we have an evolving target domain? Right? So here, what we talk about is we talk about incremental domain adaptation. So we have to kind of adapt to the change into my target domain. And this could also be something like, you have some real life situation in which I'm just acquiring data all the time. And of course, my target domain is changing. So I have to adapt to that type of thing. And then another thing is that the target is a compound of multiple domains without domain labels. Right, so in some cases, I mean, again, so far the assumption was that the target domain would be something compact, but it may be having different modes. And in that case, of course, you have what we call the open compound domain adaptation. So you see there are many recent papers trying to address this kind of real world situation. This open compound could also be considered as a multi-target domain adaptation in the end, right? But of course, there you know that the targets are different. Here you have to kind of understand that, that you have different modes. So maybe a simple distribution will not work for the target domain, but you will have a distribution with different modes. Okay, then we have another important situation in which we are in a distributed setting and we need to account for the domain shift. So this will be the federated domain adaptation. And finally, this is, you have only the target metadata available. And these are some things in which they are called the predictive domain adaptation, graph relation domain adaptation, and so on. These are some of the work of Elisa and, Massimiliano Mancini. It's one of her former students. So far, so what I said, there are many works, and you see I try to make a kind of a summary of how we deal with this type of situation. So we try to kind of mimic the situation of the real life, and there are many works into this. It's a very popular domain nowadays. So if you want to publish into the top conferences, we are working on domain adaptation. It could be a good idea. The problem is that, of course, it's quite a big competition. So that's you have to be aware of that. But so far, I was talking about images. But of course, you can just go beyond image classification. So you can use domain adaptation for other kind of domains. Now, so one example, and this is something very powerful, is to use synthetic data. Right? So imagine now that I can have some sort of a simulator, like for autonomous driving, and I can get practically data for free, and I can use this one to do domain adaptation later, right? And then, of course, this is a little bit different because I'm having different type of domains. I may also not have only the visual domain, but I may consider point clouds and other kind of things. And this is what I will discuss a little bit later. Another thing, what you can do is, of course, to do domain adaptation on videos. So one good set, it's the Epic Kitchen data set, right? And here they've been evolving a lot during the last few years. Well, this is just an example. They have this, the unsupervised domain adaptation challenge. They have several, I'm not sure exactly how many kitchens in how many countries. And they do this kind of, videos like this, kind of people washing, cooking, whatever, doing all the things that you will do in the kitchen. It's very challenging. And there is a lot of label data in here, so you can train your model. But I think it's interesting to look at. I think there are, if I'm not mistaken, 4 cities in some 50 kitchens or so. So they were, and well, the group that is doing, well, there are some people from Italy. There are some people, Dima Damen in Bristol, and there are a few other groups that are working onto this Epic Kitchen stuff. Okay, so you can also say, as I said, you can also start looking into point clouds, right? So if you look into, well, now you have different situations for autonomous driving, right? So then you have this LiDAR scanning. So you have point clouds. So you want to still be able to do adaptation between things like the Kitty data set in which there is some well, it's a data set collected in, I think it's in Karlsruhe anyway. It's a German city type of scenario in which you have cars and narrow roads and so on. And then, of course, it's completely different from what you have in US, when you have large roads and, well, different type of cars, maybe no vegetation and so on. The houses are not close to the road and so on. But then, of course, you still want to be able to adapt in some way, right? So this is, you have different object differences. You have scenario differences, and you have the sensor differences. Because also there, of course, so the LiDAR sensor that we're using to Kitty data set would be completely different from what was been used in the new scene data set. Okay? So they get the same modality, but of course there is a sensor difference in there. So you still want to do adaptation. Another thing that we've been doing, so this is something that to do domain adaptation in video, trying to adapt from synthetic data. What we created this Mixamo data set in which you have, some people doing whatever flip-flops or whatever they do in there. So this is something, the good thing about that is then you can change, you see the background and everything. We put some random stuff, some random objects, you have the washing machine and all these type of things. So try to make it as different as possible. But then you have to match that stuff with this one, which will be the real image that you have. Okay, so this is a Mixamo data set. So we have about 36,000 videos. It's all available, by the way, so you can use it. We have 14 action categories. And the goal was, again, here we assume we have the same label set between source and the target. So we put these categories as the ones that are available in kinetics, and then because we wanted to do this adaptation. And then we had these 3D characters from Mixamo, so were created with Blender, and we have 6 different distinct avatars with different backgrounds, camera position, and random object in the scene. As you see here, different type of things like punching, backflipping, side kicking, running, and whatever you see there. So it's completely different from the real world. But the good thing about it is that you can just play around with it, and then you can get for free practically a lot of data. Now, capoeira, breakdancing, you can see the stupid background in there. It doesn't matter. And of course, we also did some work on this. This is one of the work that we use it to test our model. Was what is called CO2A. It's contrastive conditional domain alignment. So we start with the source and the target. We represent it together into the same space, and then from there we have the consistency loss. So these are some things that we have into the loss, and then we also use some, since it's a contrastive learning, we have to provide also some negative examples. And then, well, for each of them we are providing some other losses and some of the networking which you put together the two domains. And then, well, as usual, our numbers are better than whatever the numbers that other people have. Of course, it is much worse than the supervised examples, but still, it's working quite well. What we had, this is we have two recent papers into ECCV 2022, was on online adaptation in 3D LiDAR segmentation. This is something quite new. I mean, I think practically almost nobody did it without. And this is difficult because we wanted to make it adaptation while navigation. So you have an online adaptation, but without the source data. So it's a source-free online navigation thing that we did. And well, again, we have now video. We have the target. As you see, it's going at it's time frames that we are using, and we are extracting some geometric features and some of the shared feature between the target and the source domain that we obtain. And practically here, what we obtain, we are obtaining pseudo labels that are extracting from the points that consistently provide similar output distribution under different dropouts. So we are kind of doing some point selection. We cannot just use all the points because that will be far too expensive, and many of them will be very noisy. Right? For example, you can have occlusions and so on. So what we did here, we were kind of providing pseudo labels only for the points that are more reliable. And here again, we are using uncertainty score for thresholding, and we use a threshold that's specific for each class. So in some cases, for example, the road, the threshold would be probably lower because it's very likely that you are going to see a lot of very similar type of points for the road. But when you look at pedestrians, for example, or cars and other type of things, this is going to be far more unreliable. So, well, this is you look into the time domain and you are adapting all the time that your information is changing. We also had a new data set. It's called the SYNT4D data set. And here we are, so you are using the Carla simulator. We have 20K labeled point clouds. And we have several scenarios like a town, highway, rural area, and the city stuff. This is some example into what you have in there. And then, well, some numbers in which, well, you can see, well, in general, our model works better than the rest. I have a video of this. So this is how it's working. And you see what kind of things are detected in, so this is the SYNT4D to semantic kitty. This is in the point cloud domain. You can see for the labels are the objects that you are encountering. So like could be vehicle, pedestrians, and so on. And the labels are quite good. And this is done in real time. So if you look at our adaptation domain and ground truth, it's very, very similar. Okay, so as a summary here, there are several consolidated methodologies for closed set domain adaptation. And of course, the best result is combining them. And then there are new challenges in more realistic settings. And well, I already said about universal domain adaptation, source-free domain adaptation, and so on. And probably it's the right time to pushing towards integrating domain adaptation approaches in difficult tasks. Well, another thing that we could consider so far, it's also what we called going beyond the domain shift. Yeah, so practically what you would want is that you start training into that situation, and then the testing situation is completely different. It's not only the environment, but also the density of people, the appearance, the way they dress, and so on. So this is something that you would want to address. Right, so it's another problem because you have the domain, the training stuff, and you are kind of want to do try a different model now, so you have a semantic shift. So you are training it with particular category, and then maybe in the same domain, you want to have different category, and you want to deal with this semantic shift. So in general, what people do in order to address the semantic shift is called continual learning. Right, so you are trying to do some sequentially learning new task while being able to retain the knowledge from the past experience, right? So I'm just adding new task, new domain, new categories, while I'm still retaining what it is in before, but I don't want to, of course, forget some of the things. So here I'm updating the parameters of the network in order to perform well on a new task without degrading the performance on the old task, right? So you want to avoid this catastrophic forgetting things. And there are several approaches in continual learning. So this is, there is a survey on this type of thing. So you can see some of the continual learning methods. So you can have reply-based methods, you can have regularization-based methods, you can have parameter resolution methods, and so on. So there are quite a few recent ones. And in the reply-based methods, we are storing or generating example of the first task, which are then used in the sequential task. So this is fine because I'm kind of storing some kind of summary information from the first task, and I'm using it in the next task, and so on. And this is good, but the problem is, and I will talk a bit later, is that what if I cannot store data for privacy reasons, for example? So in that case, it's going to be more difficult, right? So I cannot probably use replay-based method. Then in the regularization-based methods, you are either penalizing some changing of the subset of parameters while learning the new task, or you are doing some sort of distillation methods. You see some of the things in there to force the network not to forget past knowledge, right? Some kind of filtering out some of the important information, and I'm keeping only that step. And then in the parameter isolation-based approaches, they are built on the idea of having task-specific set of parameters. Yeah, so here it's a reply-based method, so this is some kind of a standard mechanism. You just store or generate example of the old task and then use them in the new task, right? Then you can combine the classification loss and the distillation loss, and you maintain the sign of the example set constant. And so you update the representation, and well, after that you just combine the classification loss and distillation loss. Okay, so for the regularized-based methods, you penalize the changes of a subset of parameters while learning on new tasks. Or you are employing the distillation to force the network not to forget the past knowledge. And you see here, you are kind of imposing several things, like you are considering the weight importance, like the Fisher informator matrix, for example. You can have this elastic weight consolidation approaches. So while you are learning a new task, you constrain the weight to stay within in a region of the low error for the old task. So kind of you don't move away from what you had before. Yeah, so if you use only example of the new task, there is type of approach that is called, it's quite important, the learning without forgetting, so LWF. And this optimizes for high accuracy for the new task and for the preservation of responses on the existing task for the original network. So you make sure that you kind of respond well on the old task while you are up to optimizing for the new task. And this is what people use knowledge distillation approach, And the good thing about this type of approach is that you don't need the all task images and labels. You just keep the information that it was stored before, nothing else. And this is some parameter isolation-based methods in which you can learn task-specific binary mask. It's called the piggyback one. The other one is a progressive neural network, which instantiates a neural network for each task being solved. So you keep on kind of updating the parameters. Well, something else that is very popular, of course, is to use this transformer for continuous learning. And you have this encoded-decoding strategy. So the encoder layers are shared among all members of the dynamic network. And then you have a unique decoding layer that is also shared. And this is also specialized by a task-specific learn token to produce task-specific embeddings. Well, and then you do this in order to make sure that you are not exploding your memory stuff. So the thing that you remember, that you keep on remembering, you kind of keep it to a minimum, because this is quite important. Okay, so now what if we go to some other type of assumptions? So far, we assume that there are no limitations in terms of computation resources or privacy. Yeah, so as I said, for the relay-based method, you could just store information in there. But this could have problems with privacy. So you want to make sure that this information is not stored. Some labels may be available, right? So you may have, so this is an assumption, but it's not always true. And then you can also, the assumption would be that learning a single or multiple classifier that solve all the tasks, right? So then you have things like the scarcity of resources. So you want to do this type of information, this type of adaptation in which you have some constraints. So you want to do it on the mobile network or IoT devices, or you have some privacy constraints in there. So what you want there, so imagine that you have a pre-trained model on a cloud and then deploy it on some small devices, right? Probably with limited connectivity, but you still want the network to keep learning adaptively. Right, so this is quite an important problem in there. So if you can do, cope in this situation without additional moment, that will be quite strong. But then, of course, you may have problem with extreme sources, with the scarcity of resources becoming available. Well, so you can have, for example, if you get data from the satellite, you have a lot of data, so you cannot store this data. So you have to cope with this type of situation. Right, so this is something that, this is a work by Elisa and her students, in which they call it the memory-constrained online continual learning. Yeah, so this is a paper at previous ECCV. And what is they said that the continual learning solutions that were available so far were not compatible with this new scenario. And so like in the replay-based method, you don't want to store previous training samples, right? Or you cannot even train a generator in some way. So what you do here, what you will need to do is to try to kind of do this domain adaptation in which you are kind of releasing all the constraints and all the connectivity what you would have into a memory constrained online continual learning. Right, so then most of the methods violate the constraints that we had before. One solution was to use this, what they call the batch level distillation. So you use only the data in a current batch, and there are two-stage pipelines. So one will be a warm-up pipeline in which practically you prepare the network distillation and take a small gradient step, preparing the network for the knowledge distillation. And then there is a joint training stage in which you dynamically weigh distillation and do some new task learning. So you have the first warm-up stage, and then you use this information to do the joint training stage. Okay, and then you have some of the losses, the gradient descent, and so on. So some of the results in here, well, well, again, BLD works better than the rest of the approaches. So you are, again, in the memory constrained continual learning situation. And, there were different type of data set, different type sequences, memory overhead, and so on. And you can try C there, and depending on the constraints you have, you can obtain different type of numbers. But in average, our approach, so their approach, it's better. So just going closer to finishing, you can have also some other type of situation in which you have no labels at all, right? So availability of labels when learning online or sequentially, it's quite unlikely. Or you can also focus on learning good visual representations, right? So you want to train a classifier on, or even fine-tuning a pre-trained feature extraction on a downstream task that takes literally seconds to modern hardware. And here comes the self-supervised learning, right? So here in the self-supervised learning, we are exploiting the interesting structure of the data to pre-train strong features. And then practically the objective of this pre-training is to find parameters that are minimizing that loss. And then, of course, there are different type of self-supervised approaches, so contrastive-based, right? So you have some instance discrimination, invariance augmentation, and negatives. You have consistency-based, in which you have no negatives, but you have only invariance to different augmentation of the data. You have the correlation-based approaches, which is invariance to augmentation and redundancy reduction, and the clustering-based approaches. So you see there are different losses that are employed for different approaches. So you could also have things like a problem like this, in which you have the continual self-supervised learning, in which you are learning strong feature from streams of unlabeled data. And in that case, you are just estimating the loss on the expectation part. Yeah, so again, here you have different type of losses depending on what type of approaches that you are considering. You see there are quite a few of them, so Barlow twins, Dino, and so on. And we try to exhibit different losses and feature normalization then interfere with continual regularization losses and vice versa. Yeah, so this is one approach that was done by, this is a new work by Elisa, in which they were using two simple ideas. So you have a predictor network that maps the current state of the representation to the past state, and then a family of adaptive distillation losses that is inherited from the self-supervised learning literature. And then we use the same loss for distillation representation learning. Some of the things that, I mean, just to finish, one thing that I wanted to, I want to stress, it's the fact that we publish, that this is, it's kind of a recent, it's in the Journal of Machine Learning Research. It's called the SoloLearn data set. So it's a self-supervised learning library. And you have tons of good stuff in there. So you have, we implemented 17 methods. We have the NVIDIA DALI data loading. You have automatic UMAP. You have all these type of things. And you can play around with it. And it's fully available for everyone. So it's quite, it's been extremely popular. I think it's about a year old, but it's been downloaded and been used by many, many people. So it's also possible, if you have your own approaches, to add onto this library. So it's kind of dynamically changing library. So you can change it. It is actually for everyone. And I think it has become more like a standard for these self-supervised learning approaches. So, well, there are some of the results that you can have depending on class incremental, depending on the approaches that you have. Well, approach is ours, fine-tuning. You see, we have much better results than just using simple fine-tuning. So, well, again, some tables, results, and so on. So just in summary, so again, continual learning as domain adaptation is widely studied. We have different strategies for doing this. And then, well, it's something very, very powerful right now to kind of put this together. So just to conclude, what is next? Well, there are several challenges that we want to do. We want to look into foundation models that are robust to many distribution shifts and may lead to substantial improvement in domain adaptation. for example, image text augmentation, standard augmentation, and so on. You can have something that, and we've been working quite a lot on, we had several works in the last CVPRs, ICCV, on novel class discovery. So here, practically, you just look into the unlabeled data of new classes, and you just understand the difference between the new classes and the old classes, and you are kind of doing the adaptation, the training, only on the new classes. So you are discovering what is the new classes online, and you try to adapt on that particular approaches. And well, you can have several things. You can even have, so this is something that we proposed recently, what is called this class increment and novel class discovery. And you can do these things quite a lot. Then, domain adaptation and continual learning have been considered as separate problems, but now the idea would be to kind of put them together and try to obtain better results of putting together. So practically what you want to do is to develop adaptive learning systems that continuously learn without supervision in ever-challenging environment. So this is all I wanted to talk about. I realized that I went very fast through a lot of things. I even skipped some of the slides, but the slides will be available. I have a list of many references. I cannot tell you exactly. So you can use it and try to see. I think it's kind of very, very popular domain. It's a lot of margin to improve. So if you are interested in this type of things, just go and work. I mean, again, as I try to illustrate here, so far many people use a lot of assumptions, but if you start relaxing them, it's getting more challenging, but on the other hand, it's also giving you a large margin for improvement, because you can really try to achieve something very, very important. So, if you have questions.
Thanks, Nicu. Let us take questions.
Hello, so thank you very much for the presentation. My question is not 100% related to the presentation, but I was just wondering what's your take on multitask learning?
Oh, multitask learning has been around for many years, and I think it's still there, and I think we should really work on it, for sure. Absolutely. It's something that is it's still popular, and it's, well, I mean, some of the things that we've done are similar to multitask learning, are related to this. So let's say multitask learning has been even before the deep learning anyway, so that was probably that was the only approach that you could do before having the deep learning models, the strong models. I mean, you would have to do multitask learning. But it doesn't mean that now that we do the deep learning stuff, you cannot use the multitask learning approach. Yeah, so just. It's here.
Oh, sorry.
So I have a question about, I think you briefly mentioned it. What do you think about negative transfer? So how can you make sure that domain adaptation or domain shift, it's actually worth it instead of training a model from scratch?
No, it's a very good question. I mean, well, if you make sure that you are regularizing well and you are not overfitting and so on, it should not happen. But indeed, I mean, it could always happen. So you have to make sure that you have to test it all the time. I don't think that there is any recipe to make sure that you are avoiding. Somehow it's some kind of magic. You know, you need to make sure that the batches are well done. You need to make sure that the data is well prepared. But I'm not sure. But negative transfer is indeed one of the main problems it is that you would have.
Yeah, thank you. So maybe another kind of question that's slightly unrelated. I've been like, I'm aware of this kind of causal domain adaptation. So do you think, I am not sure whether you've had experience with it. What is your opinion on this kind of causal inference on
We
the
have
model?
not worked on this, but for sure it's important. I mean, if you can, I mean, in some cases, causal processes are quite important because it's giving you a very, very strong prior. So if you have this information and you know about it, you should definitely use it. I mean, that's definitely like, it's quite important. And I think it was yesterday, I think it was Paul Ludovic saying that, you know, if you have these causal things or the physical laws, you should definitely use them. So it just doesn't make sense. In some cases, it doesn't make sense to learn them if you know that they are in there, so nothing will beat physics. So using causal things, yes, if you know it that it's really causal, then you should definitely use it. We haven't done it, actually. But,
Yeah, okay, thank you.
Mm-hmm.
Okay. Before we thank Nicu, let us have a short break while Chavi is setting up for the next talk, and then I think we'll have tea afterwards, and then Nicu will be around for more questions. Okay, so Nicu, this was your last talk to us, but he will be around.
I'll be around, yes.
Thank you very much.
Thank you, guys.